Welcome. In this video, we'll walk through solving a trigonometric equation. By the end of our session, you will be able to solve complex trigonometric equations by using identities to rewrite them in a more familiar quadratic form. Specifically, our goal is to find the maximum angle x between 0 and 360 degrees that satisfies the equation cosine squared of 2x plus the square root of 3 sine of 2x minus 7 over 4 equals 0. Let's begin by taking a look at our equation. We have cosine squared of 2x and sine of 2x. Notice that the arguments of the trigonometric functions are both 2x. The equation is cosine squared of 2x plus the square root of 3 sine of 2x minus 7 over 4 equals 0. This is a good start, but we can't solve it directly because we have two different functions, cosine and sine, in the same equation. To make it solvable, we need to express everything in terms of just one function. We can do this using a fundamental trigonometric identity. Remember the Pythagorean identity? It states that cosine squared of any angle, let's call it theta, plus sine squared of that same angle theta, is always equal to 1. This means the sum of the squares of the cosine and sine of the same angle is always 1. We can rearrange this identity to help us. If we subtract sine squared theta from both sides, we get that cosine squared theta is equal to 1 minus sine squared theta. This rearrangement, cosine squared theta equals 1 minus sine squared theta, is the key to simplifying our equation. Now we can apply this directly to our equation. Our angle is 2x. So we can replace cosine squared of 2x with 1 minus sine squared of 2x. This substitution gives us a new equation. In parentheses, 1 minus sine squared of 2x plus square root of 3 sine of 2x minus 7 over 4 equals 0. Notice how the equation now only contains the sine function. By using that Pythagorean identity, we've successfully rewritten the equation using only one type of trigonometric function. This is an essential first step in solving this problem. Great. Now that we have the equation in terms of just the sine function, we can simplify it. Let's start by rearranging the terms and combining any constant values. Our current equation is 1 minus sine squared of 2x plus square root of 3 sine of 2x minus 7 over 4 equals 0. First, let's group the constant terms 1 and 7, 4 together. We can rewrite the equation as negative sine squared of 2x plus square root of 3 sine of 2x plus 1 minus 7 over 4 all equals 0. Let's combine those constants. 1 is the same as 4, 4, so 4, 4 minus 7, 4 is negative 3, 4. Combining the constants gives us negative 3, 4. The equation is now negative sine squared of 2x plus square root of 3 sine of 2x minus 3/4 equals 0. To make it look more like a standard quadratic equation, where the highest power term is positive, let's multiply the entire equation by 1. Multiplying by 1 changes the sign of every term. The negative sine squared becomes positive, the positive square root of 3 sine becomes negative, and the negative 3/4 becomes positive. This simplified equation, sine squared of 2x minus square root of 3 sine of 2x plus 3/4 equals 0, is a quadratic equation where the variable is actually sine of 2x. This transformation into a quadratic form is a powerful technique. It shows that by using an identity and some algebra, we can turn a complicated trig equation into something more familiar and solvable. Now we have a quadratic equation involving sine. It can be easier to see this if we make a simple substitution. Let's define a new variable, y, to be equal to sine of 2x. So wherever we see sine of 2x in our equation, we'll replace it with y. This transforms our equation into y squared minus the square root of 3 times y plus 3/4 equals 0. See how it's a standard quadratic equation in the variable y? We can solve this using the quadratic formula. The formula states that for an equation x squared plus bx plus c equals 0, the solutions are x equals negative b plus or minus the square root of b squared minus 4x all over 2. In our equation, y squared minus square root of 3y plus 3/4 equals 0, we can identify our a, b, and c, t. Here a is the coefficient of y squared, which is 1. B is the coefficient of y, which is negative square root of 3, and c is the constant term, 3/4. Now, let's plug these values into the quadratic formula. We get y equals negative square root of 3 plus or minus the square root of negative square root of 3 squared minus 4 times 1 times 3/4, all divided by 2 times 1. By making the substitution and applying the quadratic formula, we have set ourselves up to find the values for y, which will then tell us the values for sine of 2x. Now let's simplify the quadratic formula we just set up to find the values for y. We have y equals the expression you see on the board. Let's simplify this step by step. In the numerator, negative square root of 3 is just square root of 3, so the numerator starts with square root of 3. In the part under the square root, called the discriminant, negative square root of 3 squared is positive 3, and negative 4 times 1 times 3/4. The 4 in the numerator and the 4 in the denominator cancel out, leaving us with just minus 3. Inside the square root, 3 minus 3 is 0. The square root of 0 is 0. So the entire term with the plus or minus sign vanishes. We are left with y equals square root of 3 divided by 2. We found a single solution for y. Since y was our placeholder for sine of 2x, this means that sine of 2x must be equal to the square root of 3 over 2. This step was crucial. By carefully applying the quadratic formula, we found that our original complex equation simplifies down to a single, much easier trigonometric equation. Sine of 2x equals square root of 3 over 2. Now we need to solve the equation sine of 2x equals square root of 3 over 2 for the variable x. Let's remember the range for our final answer. We need to find x in the range from 0 to 360 degrees, including the endpoints. This means x can be any angle from 0 to 360 degrees. However, our equation has 2x, not x. This means we first need to find the possible values for 2x and then solve for x. First, let's solve for the possible angles where the sine is positive and equal to the square root of 3 over 2. Remember the unit circle or special triangles? Sine is positive in the first and second quadrants. The reference angle for which sine is square root of 3 over 2 is 60 degrees, or pi over 3 radians. So, in the first quadrant, theta, which is our 2x, is 60 degrees. In the second quadrant, theta is 180 minus 60, which is 120 degrees. We must also consider all possible angles. We add multiples of 360 degrees, which represent full rotations. So our general solutions for 2x are 60 degrees plus 360 times n, and 120 degrees plus 360 times n, where n is any integer. Now we can solve for x by dividing each of these solutions by 2. Dividing the first solution gives x equals 30 degrees plus 180 degrees times n. Dividing the second solution gives x equals 60 degrees plus 180 degrees times n. We've found our general solutions for x. Our final step is to find which of these solutions fall within the required range of 0 to 360 degrees, and then identify the largest one. Our general solutions are x equals 30 degrees plus 180 times n, and x equals 60 degrees plus 180 times n. And we are looking for values of x that are greater than or equal to 0 and less than or equal to 360 degrees. Let's test integer values for n, starting with 0. If n equals 0, our first solution is 30 degrees plus 0, which is 30 degrees. This is in our range. Our second solution is 60 degrees plus 0, which is 60 degrees. This is also in our range. Now, let's try n equals 1. For n equals 1, our first solution is 30 degrees plus 180 degrees, which is 210 degrees. This is also in our range. Our second solution is 60 degrees plus 180 degrees, which is 240 degrees. Again, this is a valid answer. Let's test n equals 2, just to be sure. For n equals 2, the first solution is 30 plus 360, which is 390 degrees. This is too large. The second solution is 60 plus 360, which is 420 degrees. Also too large. So we have found all the valid solutions. The solutions in our range are 30 degrees, 60 degrees, 210 degrees, and 240 degrees. Looking at this set of solutions, the largest angle is 240 degrees. Let's review what we did. We started with a complex trigonometric equation. We simplified it using a trigonometric identity, solved the resulting quadratic equation to find all general solutions for x, and finally, selected the largest one that fit our specified range. And there you have it. The maximum angle in the range 0 to 360 degrees that satisfies the equation is 240 degrees.